Hello students, this is the introduction to our new unit on torque and rotational motion. This is a physics topic which for some of you will be a good relief from the heavy biology that we've been doing so far this semester. In torque, we're going to connect to some of our learning from last year in Integrated Science 1. And in particular, we're going to ask you to remember some of the concepts of Newton's laws and apply them to a new situation with some analogies. So, back last year, you learned a lot about linear motion. You learned one of the most important tenets of basic Newtonian physics is that an object can't accelerate or decelerate unless there's a force that causes it to move. So, in the case of linear motion, what causes an object to accelerate is force. In Newton's second law, you studied an equation which helped you to relate the size of the force, the mass of the object, and the size of the acceleration it experienced. A familiar equation, hopefully for you, would be that force equals mass times acceleration. We're going to basically follow a similar format this year when we study rotational motion. The physical quantity that causes objects to rotate is not the force they experience, but rather the torque they experience. You may have heard the term torque before in truck commercials. They'll advertise the amount of torque that a truck will provide for the engine. And there is an equation similar in format to F equals ma, force equals mass times acceleration. This time it's torque equals force times the length of the lever arm, and we're going to talk about that in just a minute. The lever arm is the distance between the pivot point for an object, the object that you're considering in a problem, and where the force is applied to it. If you look in the upper left, where there's a picture of a wrench. Wrenches are very useful objects, simple machines for us, because in order to get something to rotate, it extends the lever arm that we can exert on a bolt. So if you were trying to get this bolt to turn, it would be really hard to do with your fingers, even if your fingers, let's say, had good grip, which is often part of the problem. But even if you had good grip, it would be really hard to get that bolt to turn. The wrench extends the lever arm, and in doing that, it maximizes the torque that you can apply to that bolt. Now, most of the problems that we'll see in this class related to torque will be related to a concept called equilibrium, and that's something you've heard of before. In equilibrium, we can say a couple of things. First of all, in relation to linear motion, the net force on the object that you're considering is zero. So you could be pushing or pulling on opposite sides, and those forces would cancel out. you could say that that object is in equilibrium in terms of linear motion. The new piece related to torque is that the net torque on the object is also zero. So if you are applying a wrench to a bolt and you're pushing clockwise with a certain amount of force, and someone else is pushing counterclockwise with the same lever arm and applying the same amount of force, then the net torque is also zero. In that case, the torque applied, and we're almost always going to be drawing pictures where there's a clear left side and right side. So I think it's helpful to say that the torque on the left side is equal to the torque on the right side. And we'll see a problem like that in just a second. Unless otherwise specified, every single problem we'll see in integrated science related to torque will be for objects that are in equilibrium. That is, their net force and their net torques are zero. Let's next slide. In this next slide, we have a picture of a seesaw or teeter-totter and two children sitting on it. Notice that the teeter-totter or seesaw is completely level. Now, I know at a playground that might not be the way you want to play with a seesaw or teeter-totter. You probably want it to be going up and down. But for the sake of this problem, we're going to notice that the seesaw is is in equilibrium. That is, there's no rotational motion going on. And if we can say that, then the left side torque will be equal to the right side torque. And if that's true, then we can say that the force times the lever arm on the left side would be equal to the force times the lever arm on the right side. And if you look at the picture, they're nice enough to give us both a force in newtons and a lever arm length in meters on the left side. On the right side, a force in newtons and a lever arm in meters. It's simply the product of those two. So let's see if this checks out. The force on the left side for the girl that's to the left of the pivot point is 250 newtons. The distance that she sits from the pivot point is 3 meters. The force or weight of the boy on the right side is 500 newtons. And the distance that he sits from the pivot point is 1.5 meters. And if we work this out, you could probably do this in your head. 250 times 3 is 750. The unit for torque is nothing new. It's simply the product of the force and the distance, that is the lever arm distance. It's a newton times a meter, a newton meter. 500 times 1.5 is also 750 newton meters. So this equation does indeed check out. And for any object that's in equilibrium, the left side torque is equal to the right side torque. We'll see that play out again and again tomorrow in class when we tackle some problems together. Thanks for your attention. What I'd like you to do next is to go to the links provided, all of which could be found on gigaphysics.com. There are two tutorials and a worksheet that I'd like you to try out, and bring your answers to those questions to class tomorrow. Thanks.